All right, so full disclosure, I haven't talked to Thomas at all. You're going to see very similar themes, but coming from a very different angle. My particularly strange Lovian title is, I guess I put it together in a fit of pith, I think, when the administration decided to pull out of Paris. So I'm going to start. I'm actually going to motivate my talk by talking just a little bit about the National Climate Assessment, which is an important thing that the oceanographic, marine science, and really, a broad section of the scientific community in the U.S. is working on right now. I'm going to talk specifically about marine heat waves, and then I have somewhat of a surprise. So my co-authors on the first bullet are working with me on an NSF Coastal Seas project that's been motivated by the 2012 heat wave that we had here in the Gulf of Maine. The folks on the bottom bullet are my co-authors for the Oceans chapter of the Climate Assessment, and they very much influenced my motivation to think about heat waves and surprises. So what is this thing called the National Climate Assessment? Well, it was established by your U.S. Congress back when they passed laws in the 1980s. Actually, we hope they stop. But anyway, that's just... but really, the point is for us, every 4 years, the scientific community of the United States is supposed to come up with our best assessment of how climate change impacts the resources and things that people in the United States care about. So assessments were completed in 2000, 2009, and 2014. Another one is underway, supposed to be completed in 2018. So chapter drafts were just submitted a couple of weeks ago. They're going to go through some technical scrubbing and some editing and basically the internal editing. Then they'll be available for public comment in the fall and in the winter, and with the final version coming out in the end of summer. And I really want to flag this public comment period. You're going to see requests coming out, hopefully, on all of the listservs that you subscribe to. I tend to always ignore these things and assume other people are going to handle it. But as you know, climate change is not exactly the most popular topic in the country right now. There's a very organized group of people out there, most of them spending their time watching things like InfoWars and get very fired up about things that they don't really understand. They are just as likely to comment on this as you are. So it will be really helpful to those of us who are working on these chapters if you go through, even if you're not saying, cite my paper here or do this over here, if you just come in and say, this is a really important message, you got it right, that's going to be very helpful for us as we have to go through all of the public comments. So getting comments from the scientific community is really important. So I'm the lead author of the Oceans and Marine Resources chapter. This is the second time that the NCA has included an Oceans chapter. And our goal is really to help make climate change real to people in the United States through the lens of the ocean. So there's a bit of a shift from the previous NCA in that we really are thinking about the impacts on people and on human communities, and in this case, through the lens of ocean ecosystems. So our three key messages are that ecosystems are being disrupted, and these are drafts, so I'm not putting the full text up. But the basic theme, much like the prior question, we're seeing irreversible losses of things like coral reefs and sea ice habitat, so ecosystem disruptions. We're seeing impacts on fisheries, very much similar to what Thomas talked about and concerns over those projections, although that one has a bit of a positive spin, and then there's been real improvements and strategies for how we might manage fisheries in a changing climate. And then heat waves and events emerge as a theme, in no small part because it's something we've seen quite a bit recently. So Alistair Hobday came up with a definition of marine heat waves in 2016. And basically, you have some... I'm not getting the angle. Oh, I'm blocking it with my finger. There we go. All right, so we have some sort of climatological reference, right? Your average conditions. Then you have your actual temperatures, and if your actual temperatures exceed some threshold for a fixed amount of time, you declare it to be a heat wave. So I ran Alistair's algorithm and looked at just the days where you're above a heat wave threshold in a calendar year. So 2011, the heat wave in Australia. 2012, the heat wave that we had in the North Atlantic. The blob in 2015. Okay, so lots of events are going on, and it's notable that that the term marine heat wave didn't enter the literature until 2000, I believe until after the 2011 event in Australia. But all of these events have very similar impacts that we're seeing. In all cases, we're seeing highly mobile species on the move. So in the North Atlantic, we saw black sea bass, which are normally caught down here in Buzzards Bay and Long Island Sound, moving up to the coast of Maine. We saw longfin squid that are normally caught here in sort of these yellow dots, also up in the coast of Maine. We've seen impacts, direct impacts on fisheries. With the blob event, Dungeness crab was the big impact. In our region, lobster was the one that's gotten the most attention. This is showing the annual cycle of lobster landings just in Maine. Very seasonal because as waters warm up, the lobsters get more active, they get easier to catch, and they migrate inshore. And so catch rates go up. In 2012, they went up about a month ahead of schedule because water temperature was running about a month ahead of schedule. We also saw the lowest cod recruitment in 2012 as well. But we then have seen impacts on people, and we really can make the case that the physical changes in the ocean go through the ecosystem and affect people. So for lobster, while we had very high and very early landings, the supply chain wasn't ready for all of the soft-shell lobster that was coming on the market at the time. The price collapsed, and it was actually a very challenging year for many lobstermen in Maine. There's a really excellent documentary that the Discovery Channel put out about the challenges facing cod fishermen. So the other thing that's a common theme when people describe these heat waves is that we're always trying to look at, well, what was the proximal driver? And so we look at things like NAO and the AMO and these natural cycles, and in many cases you can see that the heat waves are coming because you have an interaction or basically multiple cycles that are adding together. So in the North Atlantic heat wave, Ki Chen talked about movements in the jet stream that look a lot like North Atlantic oscillation type effects. There was preconditioning with warmer deep water in the Gulf of Maine that Dave Townsend has talked about that looks more like an AMO type effect. Okay, so these two were adding together to give us the intense temperatures that we had in 2012. And so that leads to this idea that I think many of us had, and this has certainly, I think, been a major part of my career where I've written a lot of proposals that have said, I'm going to study something like the AMO or the NAO, and by understanding that variability, it's going to tell me, it's going to help us learn about climate change. So the idea is that we have natural variability. Here I'm depicting it as two frequencies that are going to add together and occasionally give you these heat spikes. We can then add that to a global warming trend, and that we essentially have an additive effect. And if you were to remove the trend, you would see that the heat spikes are occurring at roughly the same intervals. Okay? If you use a fixed climatology, which I think is pretty similar to what Thomas was doing, you end up with heat spikes getting more frequent. Okay? But if you account for that trend, you should be able to say, well, yeah, things aren't really changing. Things are amping up. And the frequency of the natural variability is staying more or less the same. The other bit of linear thinking that goes on and when people are doing this kind of work, and it's very much in the Mills et al. Paper that I was a co-author on, one of the things we were saying was that the temperatures that we experienced in the Gulf of Maine in 2012 were like the temperatures that we're forecasting for mean conditions of 2070. So that should give us some idea of what the mean conditions might be. So that when we encounter similar temperatures in the future, that we're going to see similar effects. Okay? So additive effects and repeatable impacts. So I'm going to talk very quickly about repeatable impact and then move to the additive effects. So for the repeatable impacts, we had a natural experiment where 2016, only 4 years after 2012, was almost as warm in the Gulf of Maine. Other than a few days in the spring, the red and the light black line, they're pretty much tracking one another. And we had very, very similar conditions in 2016 that we had in 2012. We had a very similar lobster fishery in terms of when landings were occurring and also how many landings were occurring. Okay, so that says that the lobsters were doing their thing. They were sort of getting on the move and migrating and molting at roughly the same time, or at least the same temperatures that they did in 2012, and that the fishery was there to catch them. But the price, which is the red line here in 2016, stayed really high, whereas in 2012 we had that collapse in price. So what that says is that the lobster fishery adapted. So the 2012 event caused changes in the lobster industry that allowed them then to absorb the influx of soft-shell lobster in 2016 and be able to move them and sell them in a way that kept prices high and kept lobstermen happy. So humans, we can learn from our mistakes sometimes, but our expectations can be colored by the past. And so while 2012 was a surprise, and we think that the lobster industry in Maine adapted and that we have better supply chains and so we can support better prices, that doesn't mean that if we get the next kind of 2012 event that suddenly we'll be really good at it, right? It's that we're adapting, but we're sort of adapting to whatever the maximum that we've experienced has been. You can think of ecosystems in a similar way. So from the point of view of a particular species, this isn't going to apply, but if you think about an ecosystem or a community, they're also going to evolve. And you might expect that there's some stability over time in these ecosystems. But an ecosystem that has black sea bass is going to function differently than one without. An ecosystem with longfin squid is going to function differently than one without. These are very much themes that Andrew Barton was addressing in his PNAS paper on the shuffles and shifts in the phytoplankton community. Okay, so now I want to talk about surprises. So I'm going to use a slightly different definition. It's inspired by the Hobday et al. Definition. But I'm going to define a surprise as an event that is unlikely based on recent conditions. But I'm going to use a 30-year rolling climatology. So I'm going to try to capture some of that global warming trend and remove it and just look at the noise on top of that trend. And I'm going to define an event, and I'm looking at annual events where the probability is about 0.03. Okay, so it's about 2 standard deviations away from the mean. But the nice thing is that if you assume normality, which works pretty well with sea surface temperature, is that you can actually calculate a theoretical probability of a surprise accounting for a trend. Okay, so how this works is that you have a trend. We assume that there's noise about that trend, but that noise stays the same, so that we're not changing the standard deviation over the course of our time series relative to that trend. So nature rolls the dice. You get actual realized temperatures. And then we can sort of pool that together and figure out the mean and the variance over that reference period. And then we look in the final year and say, did we reach, were we at an event that was above say the 97% threshold, which would be about right there in that distribution. And so this example here has very low year-to-year variability, and a very steep rate. So we can map the probability surface as a function of the variance in the trend. So if you pick a particular variance like 0.15 and you follow it up as you increase the trend, you see that you have increasing probabilities of having a surprise. But at some point you begin to fall off, and that's because the trend is so big that it's basically blowing up your variance. And so you end up saying that extreme events become more likely. So there's sort of this kind of optimum place here that happens to saturate with a probability of about 0.2 within the range of variance and trends that we're seeing in the ocean and the range of variability that we're seeing. Where you have your maximum potential of having a surprise. So what are we seeing? Well, if you calculate that theoretical probability of surprise, so again, what I do is I look at a 30-year period, I look at the trend, and I look at the variance over that period, and I say how likely is the 31st year to qualify as a surprise based on the prior 30 years statistics. So the probability, as you might expect, starts low, and it gets higher, okay, up to about 0.11 in 2016. We also had a period in the 1940s where we had kind of a warmer climate, and we actually increased the probability, the estimated probability of surprises during that period, and we've only recently exceeded that probability. If you look at the realized probability, so here I'm looking across the 65 LMEs, 65 large marine ecosystems, and I'm looking at the frequency of the number of LMEs, the proportion of LMEs that are in a surprised state in any one year. And you see that it more or less tracks the predicted probabilities. We have a few more here. We have less in the 60s. And then they both increase together throughout the 60s and 80s. But notice how many more surprises we're getting after 1998 than we would expect. So the question is that number of surprises surprising? Well, in one way, because it's above the probability, you would say yes, this is more than we're seeing, and it's more than really we've seen within the historical record. We can get another crack at this by looking at some of the climate models. So here I'm showing the CMIP5 ensemble of 27 different climate models, going through and looking at the probabilities, or sorry, this is the frequency of events in those models. Notice how it has the same temporal signal, but doesn't get anywhere near as high. And then look at how that relates to the predicted probabilities. So the calculated probabilities and the frequencies are tracking one another more or less the same. We don't see examples in the climate simulations where we get this really large divergence. Okay? So something really surprising is going on. What is it? Well, we can begin to get an answer by starting to look at the spatial pattern. So here's that 1940s warm period. At the top are the frequency of events in the large marine ecosystems. Here's the estimated probability of events averaged over that period. You can see that the model was saying that we should probably have a lot of events in the Barents Sea, a moderate number of events in kind of tropical low latitudes, and very few events in Australia. We did all right getting Australia right. Lots in the Caribbean, and not a lot going on here. We can take the difference between the two, and you get this kind of red and blue quilt, where you have, so you have some red, you have some blue, and more or less the red and the blue are more or less the same. There are actually slightly more blue regions where we overestimated the number of heat waves than realized than there are red regions. Okay, so now you can look at the last 19 or so years. We were saying that, yeah, there should be a lot in the Barents Sea, there should be a lot in the Mediterranean, there should be a moderate amount at mid-latitudes, and in general, the probability of surprises is higher everywhere than it was in the past. But we have lots of them in lots of places. So the North Atlantic and the Arctic stand out, the Caribbean stands out, Australia stands out, okay? So this is the other piece that's surprising to me, is that I would expect that if what we're seeing is essentially kind of say a shift in the PDO or the AMO or one of these natural modes, and so that you're getting some sort of curvature in the temperature that this linear model is not able to account for, that if we were seeing something like that, we would expect to see a logical spatial pattern. We would expect to see, for example, a PDO pattern in the Pacific or something in the Atlantic. I don't think you would expect to see this global pattern by just the normal natural modes of climate variability. So I think something really unusual is going on, something that is rather surprising. So what could this be? Frankly, I don't have the answer, but I'm going to give a couple of things that we're thinking about. One is that natural cycles are no longer natural. In Di Lorenzo and Mantua's paper on the blob event, on the 2015-2016 event, did some really interesting analysis similar to what Thomas was doing with the large ensembles, large climate ensembles, and trying to understand the variability and the frequency and the interaction with the climate modes that tended to give the blob event. And what they were suggesting is that variability in those modes is increasing and that they're interacting in ways that were unexpected. We also have the fact that, especially for the North Atlantic and also the North Pacific, is that we have an Arctic that is very different, and it's going through step changes, right? State changes, irreversible changes in the loss of sea ice that has the potential to ripple out and influence global weather patterns in ways that we haven't had a chance to experience at least in the observed data. And I would question whether we're getting these sorts of effects right in the climate models as well. So marine heat waves are occurring all over the world. Heat waves and other surprising events are becoming more common. and we would expect that. So here I'm showing the probabilities, but in a different way, showing thinking about them as return times. Where in the 1980s, we expected a heat wave roughly every 25 or 30 years in an average LME, whereas in 2016, the estimated probabilities in the climate model suggest that we should be getting heat waves in an average LME about every 10 years, and that could go down to about every 8 years. And remember, this is using a 30-year rolling climatology, so it's trying to account for the warming trend, okay? And yet we're still, even if we're trying to account for that warming trend, we essentially can't account for it fast enough, and we're still getting surprised. So the increase is expected, but the increase is surprising. So thank you very much.
Time for questions. I'll ask you a question. You mentioned that you anticipated that fisheries would adapt, so the lobster fishery was different between the first heat wave and the second. And then I think you alluded to ecosystems having some capacity for adaptation as well. I just was wondering if you could elaborate on how that occurred and what processes you were thinking about.
So for the human community, one of the things that hasn't happened is we haven't seen sort of an adaptation in terms of the management of the fishery. But what we saw was that a big part of the problem in the lobster fishery was the supply chain. So they've added more domestic capacity, they've built up markets. They basically have said, well, we're now in this new regime or this new climate where we're more likely to have high volume landings in the summer of soft shell product that has to be frozen, goes to lobster rolls, not to live lobster. And so they built up markets, which is why you can get a lobster roll at McDonald's now. So that was part of the adaptation. The biological adaptation is just so hard because you run into these kind of almost like an Euler-Lagrange sort of problem. Like, are you talking about a community just sort of translating and marching northward and more or less staying intact? Or is like in your paper, you have, yes, some of that, but some species move faster than others, and so you have the potential to get novel combinations. So there's some kind of there's some adaptation in that, a warm year can push a species in, and then a community can kind of adjust around it. But that every time you kind of keep beating on it with these increasingly frequent unexpected events, those are what I think are going to really drive a lot of the change, both in the human community and in the natural communities.
Thanks.
Hey, hi, Andrew. That was fascinating. I think I almost got it, but could you help me just one more time to explain the difference between what you did with the data to get the probabilities versus the frequencies? I'm not quite sure I
So for the frequency, what I'm doing is just looking at a 30-year block and looking at the 31st year. And so I take that 30-year block, I compute the mean, I compute the variance, and then I look at whether that 31st year is above the 97% threshold. So that's how we get the...
For each LME separately?
For each LME separately over 19 years so that we actually can get some repeatability. Okay. And then in those maps. And then for the probability, what I'm doing is I'm looking at the trend and over a 30-year period and the variance over that period and saying if you take the trend and project it forward one more year, given the statistics, how likely are you to have gotten how likely are you to get a surprising event?
Okay, so the frequency part, you don't care about the trend per se. You're not modeling the trend.
Well, right. I mean, I'm not modeling the trend in that way. No, okay. but you're trying to make you're basically calculating if there's a trend, how likely are you to say it's a heat wave or not, or to say it's a surprise.
Hey, Andy.
Thanks, Andrew.
Sorry. We've competed. Go ahead. I'll go next. Okay. So I have a question about teleconnections between oceans in some of these decadal climate oscillations like the PDO. So I just want to make sure I understood you. So you're saying that if there were changes in oscillations like the PDO, you would not have expected to see these marine heat waves all over the world. That was surprising. So my question is, we do see changes in community of zooplankton, fish in the Atlantic Ocean that seem to be tied into changes in the PDO, or we see, El Nino affects the Southern Ocean. So I was wondering if you could help me understand how that works.
Yeah, so I guess what I was trying to say is that, if you look at some of the other maps, you can kind of see that when you get some of these deviations are because you're getting a shift in, say, the PDO, and so you get blocks of color along the, say the west, the west along the west coast of North America that look like the PDO region, and we don't see in the past when there's a PDO shift that you're sort of seeing the disruption everywhere. It really seems to be highly in the PDO region because we're really talking about the SST trends. So yeah, there are connections. I mean, El Nino is a big one, right? That does kind of ripple around the world. But El Ninos are actually pretty short relative to this 30 years that we're picking up. So the fact that we saw a jump in 1998 is almost certainly due to that El Nino, but we should be pricing that in, right? We should be pricing that warm El Nino into the trends and into the variance. And even though we're doing that, I'm doing that in those calculations, we're still getting surprising temperatures.
Take one more. I think there was a question in the back, right? Yeah.
So that was closely related to my question, which is how the shape that you're using for the assumption related to Heidi's question on how often you're going to deviate and what the shape, use the same shape every single time. So how did you account for duration, and how did you had like a normal shape there, right? That was every single time. How much is your assumptions relying upon those items?
So the assumption of normality is, if we were to change how we're assuming the heat waves are related to one another, you might change the statistics. One of the things we have I have started looking at is the assumption that you have a linear trend, because we know that not everything is linear. And in the North Atlantic, that kind of ring around the North Atlantic and in the Arctic, the curvature seems to explain some of the deviations between the observed, some of the reasons why we're seeing more than what the probability would suggest. So if your temperature bends, that can give you a higher we would expect to see more than what this linear model is projecting. But it doesn't explain everywhere. And Australia really stands out as the place that I can't explain. That it just seems to be that they are getting more of these, they're getting more frequent and more intense events. And I can't see an obvious answer. Potentially, yeah. I mean, I guess that would be another one. You could use I suppose a different distribution that would have a longer tail. It's an interesting idea.
Well, I'd like to thank Andy for a very great talk. So thank you for coming.